Welcome to Mathematical Foundations of Robotics Lecture 1, where we will introduce some preliminaries to start our study of analysis. These preliminaries will consist of a review of elementary logic, which for us will be just a way of formalizing common sense, and we will review sets and functions. Then we'll pass to natural numbers and the strictly correlated idea of induction. Then we'll introduce real numbers, and finally we'll give a few examples of classic elementary functions like the exponential, trigonometric functions, and so on and so forth. So let's start with a review of elementary logic, and we'll start by defining propositions, predicates, and quantifiers. So, what is a proposition? A proposition is a sentence that can be either true or false. No other. So, just to give an example of a proposition, if we say the room temperature is between 10 degrees Celsius and 40 degrees Celsius, well, this seems to be a true statement, right? Because we can check if the temperature is indeed within this range. So this sentence is a proposition because we can check that this is indeed a true proposition. If we say that for each human being on Earth there is a robot, well, this seems to be quite unlikely. So we can assign a false value to this sentence, so we can say that this sentence is another proposition because we can establish if this is true or false. As a final example, if we say that every human being is composed of an even number of cells, well, this is something which is very difficult to check, so we cannot assign any true or false value to this sentence. So this third example does not represent a proposition itself, but it is just a sentence of which we cannot establish if it is true or false. Now, each proposition can be, in general, is indicated by using a capital letters. So we could say that this first proposition is P, this second proposition is Q, and this third proposition might be R, for example. If a proposition depends on parameters, and if its true or false value depends on these parameters, we obtain a predicate. So a predicate is a proposition which can be true or false depending on the values of its parameters. For example, if we consider the following predicate that depends on the parameter x, x squared larger than or equal to 10. Well, this predicate turns out to be true if x is equal to 100, but is false if x is equal to 1. So this is just an example of predicate, because its value clearly depends on its true or false value depends on the value that x is taking. We can have a predicate that depends on more than one parameter. For example, consider the following predicate: Q of R O. So the robot R is equipped with the sensor S. Now we have S, R and S, which act as parameters for the predicate Q of R O. Sorry, this is an S. Okay, so the robot R is equipped with the sensor S. So we have a predicate that depends on two parameters. We can also have three parameters. Consider, for example, the following predicate: R of U, V, and W. And this predicate can be U less than or equal V plus W. If we have U equal 1, V equal 2, and W equal 3, this is certainly a true predicate, a true proposition. So you see that depending on the values of the parameters, the predicate become a true or false proposition. The predicate by itself clearly does not have its own value of truth. We cannot say that the predicate is true or false, but we need to identify exactly the values of the parameters. However, there is a way of transforming a predicate into a proposition without specifying what are the values that the parameters are taking, and this is obtained by using the quantifiers. Now, there are two types of quantifiers: the universal quantifiers, which is represented by this symbol, just a flipped capital A, which is read as for every, and then we have another quantifier, which is the existence quantifier represented with the flipped E, which is read now as there exists at least. And finally, there is a further specification of quantifiers, which is the uniqueness quantifier, which is basically just another further specification of the existence quantifier, and it is represented in this way, which can be read as there exists a unique. Instead of giving a generic definition, maybe it is just better if we just give examples of how to use these quantifiers. Consider once again the predicate p of x depending on one parameter x that is we have already seen previously, x squared larger than or equal to 10. So this is a predicate, so we cannot attach any true or false value to the predicate, but we can transform this into a new proposition, and this proposition can be there exists at least one x into the natural numbers such that x to the square is larger than or equal to 10. So let me read this again. We are using the existence quantifier, and we are saying that there exists at least one natural numbers such that this natural number squared is larger than or equal to 10. Well, this is certainly true, because we know that there will be not one but infinitely many natural numbers such that x to the square is larger than or equal to 10. So we have now a proposition, because we can say that this proposition is true. Notice that we have used this symbol, this comma, and we read this comma as such that. This comma doesn't play a specific role from the logic point of view, but it is just useful to give flow to the proposition itself. If we instead use the other quantifier, which is for every x natural numbers, we can say that x to the square is larger than or equal to 10. Well, in this case we have a new proposition, but this is definitely false, because it is not true that for every natural numbers x to the square is larger than or equal to 10. So of course we can do the same. We can build a proposition also starting from the other predicate with two parameters. We had introduced q of r and s, and this predicate was the robot r is equipped with the sensor S. If we apply now quantifiers, we can build a new proposition. There exists at least one robot R such that for every sensor S, Q, R, S. So we are saying there exists at least one robot that for every sensor you consider, it is mounted on that robot. And this is something which is likely to be false, because we cannot expect that there is one robot that uses all possible sensors available. What happens if we invert the position of the two quantifiers? Because you see, in this case, we have just used the existence quantifiers and the universal quantifiers in this specific order. Let's just invert the position. Let's write for every sensor S, there exists a robot R such that Q of RS. Well, the meaning of this proposition is totally different. We are saying now that for every sensor S, there exists at least one robot R that uses that sensor, and this is likely to be true. Quantifiers are a tool that is able to build a new proposition out of a predicate. There is another way of building a new proposition from an old one, which is the so-called negation operator, and this is a unary operator because it acts on a single proposition. Let me give you an example. Let's suppose that we have the proposition P, the door is closed. Now, let's suppose that this proposition is true. The negated P, the negation of P, which is represented by this symbol, which is the unary operator negation applied to P, is building a new proposition, not P, which is now the door is not closed. And of course, if P is true, not P is false. Of course, this is inverted. If P would be false, then not P would be true. The negation operator can also be applied to a predicate. Let's consider, for example, this predicate. We have a predicate C with the parameters D, which is the door D, and this is the parameter. The door D is closed. We realize this is a predicate with one parameters D, and therefore we cannot establish if this is a true or false proposition. However, from this predicate, we can build the proposition there exists at least one door D such that C of D, and this is very likely to be a true proposition because there would be at least one door such that that door is closed. Now the problem is, can we build the negation of this proposition? So can we build, and let's say that this new proposition, we call this new proposition Q. So the problem is, can we build not Q? Well, if Q is true, not Q need to be false. So what is the negation of the fact that there exists at least one door that is closed? Well, the fact that every door is open. So we can just say for every door D is not true that C of D is true, right? So, and in fact, we see that if Q is true, this is false. In fact, saying that Q is true means that there exists at least one door that is closed. And the opposite of this is saying that for every door, that door is open, so there will be no door which is closed. Okay, so this suggests a general rule for building the negation of a predicate. So we can say that in general, if we start with the proposition like there exists at least one x such that p of x, the negation of this proposition is for every x not p of x. We can remove the comma. So as you see, what we have done, we have taken the existence quantifier and we have replaced with the universal quantifiers. Then we have taken the predicate p of x and we have replaced with its negated version. Of course, we can do the same if we start with the proposition with the universal quantifier for every x p of x. Well, the negation of this proposition would be obtained by just replacing the universal quantifier with the existence quantifier and p of x with the not p of x. Let's try to build an example, a more complex example to apply these rules. Let's consider this example. We have this predicate. Every day there is at least one robot that fails its task. Let's say rather than day, on every mission there is at least one robot that fails its task. This is a sentence in common language. Let's try to translate this into formal language, into a proposition then. We can say that for every M, where M stands for mission, there exists at least one robot R such that for every task T, the following predicate is true. Fail M, R, and T. So this is just a predicate that that for the mission M, the robot R fails the task T. Good. So now that we have this proposition, we can try to build the negation of this proposition. So let's say that we consider this to be a proposition P. So we want to build the proposition not P. We can say there exists at least one M such that for every robot R there exists at least one task T such that not fail M, R, t. And now we can translate this back into common language. There exists at least one mission such that for every robot there is at least one task T where the robot fails. Okay, so let's summarize what we just said. Okay, we started from this original proposition. On every mission there is at least one robot that fails its task. So we are assuming that in any possible mission that we can think of, for example a robotic exploration, there exists at least one of the robot that is involved in the mission that is failing its task. Now, translating this into formal language, we got for every mission we can think of, there exists at least one of the robot involved in the mission, such that for every task there must be a fail. So one of the robot involved in the mission will fail every possible task that it is assigned to the robot in that mission. We want to negate this proposition, so we want to build the not P proposition, and by just inverting the quantifiers we got that there exists at least one mission such that for every possible robot there exists at least one task such that the robot is able to execute that task, which is just like saying is not true that the robot R is failing every task T in the mission M. Good. So I hope you feel now what is the power of these rules. It would be very difficult to build this negation from the original proposition, but let's say that with some intuition, with an additional effort, we might maybe be able to build the negation, but this would become even more difficult when dealing with abstract object, because so far we have been dealing with the common language, common situation, and we can also manage to get the negation of the original proposition. This would be much more difficult when dealing with abstract objects. The negation operator is an example of an operator that is applied on a single proposition. For that reason, we call this operator unary operator. There are also examples of binary operators. And they are called binary because they act on two propositions. And for that reason, they are also called logic connectives. Now, the most important logic connectives are AND, which is represented by the symbol, this symbol, and OR, represented by this symbol. Let's say that we are given the proposition P, the map of the room contains circular objects. So we are thinking about having a map of a room where a robot is moving, and the robot needs to build a map of the environment, and we are assuming with this first proposition P that all the obstacles that are in the room are circular. Then we have another proposition Q that says the map of the room contains square objects. Okay, so we are saying now that the map only contains square objects. What will be the new proposition P and Q? The map of the room contains circular and square objects. In other words, the situation which is described by the proposition P and Q is the following. There will be both circular objects and square objects. Now, when is this proposition P and Q true? When both P and Q are true. So this is the meaning of the logic connectives AND. This is true if and only if both of the single proposition are true. The proposition P or Q instead is the map of the room contains either circular or square objects, and this is to be regarded as an inclusive, or is inclusive in the sense that the proposition P or Q is true if the room contains only circular and not square objects, it contains square objects and not circular, or it contains both circular and square objects. So all these three possible combinations give rise to a new proposition which is true. Okay, so now that we have this new proposition, we address the problem, can we build the negation of this proposition? So the new problem is, how can we express the proposition P and Q, or the proposition, the negation of P or Q? Okay, so let's start with the first one. We said that P and Q is true if and only if both P and Q are true. So that means that P and Q is false whenever at least one of the two propositions is false. So in that case, we can say that the negation of P and Q is true when at least when we must have that not P and not Q, at least one of these two needs to be verified. But of course, this is just like saying not P or not Q. So just by intuition, we came up with this rule that negating an AND proposition, we just how can we get the negation of the AND proposition? By just negating the single proposition and connecting them by an OR. It turns out that a similar rule works for the negation of the P or Q proposition, and in fact this is simply not P, not Q, connected by the AND proposition now. When working with the binary operators, it is very useful to represent all possible combination of truth value for P and Q and the new proposition in a table. For this table is called the truth table. Let's build, for example, the truth table for P and Q. We can represent all possible value of P with true and false, all possible value of Q with true and false, and then we just need to build a table to represent all possible combinations. Now, we know that if both P and Q are true, P and Q is true. And in any other possibility, we have at least one between P and Q that is false. So all other boxes are false. Let's build the truth table for P or Q. Well, again, for P, we have true or false. For Q, we have true or false. And the truth table now will contain a true whenever at least one between P and Q is true. So we have true, 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 and false. There is another truth table which is interesting, which is the so-called exclusive OR. Which is normally represented with the symbol px within a circle. Let's build this table now. We have P can be true or false, Q can be true or false, and as always, let's build all possible combination. Now it turns out that P exclusive OR Q is true if and only if only one between P and Q is true. So for example, if P is true and Q is false, this is true. If Q is true and P is false, is true, and all other combination instead contains a false. Let's give an example of the application of all these ideas, how to build a proposition in common language, and then by just using logic connectives. For example, let's consider the following proposition. In every map, there is at least one obstacle not detected by the robot. We are referring now to a situation where we have a map and the robot has to navigate autonomously through the map, trying to avoid all obstacles that can be present in the map. So clearly the robot needs to detect these obstacles in order to avoid them. And in this first proposition, we are stating that in every map there is at least one obstacle that is not detected, okay? That is not detected by the robot. Okay, let's build now the negation of this proposition. Let's say that this proposition is P. We want to build now the negation of P by just applying the usual rules about the negation of a proposition. But the first thing we need to do, of course, is translating this proposition from common language to a formal language. Okay, so let's do this. We can say that for every map M, and this is just translating this part, there is at least one obstacle O, and this is now translating this part, that is not detected. So we can say such that detect of M and O is false, which is to say not detect is true. So this is the proposition P. We are now in a good position to negate this proposition because we can just apply the formal rules to this proposition P and obtain not P, as there exists at least one map M such that for every obstacle O, detect of M and O. So let's now translate this back into common language. There exists at least one map M such that for every obstacle the robot is able to detect the obstacle. Okay, so this is one way of translating the not be proposition into common language. There exists at least one map such that for every obstacle in the map, the robot is able to detect every obstacle, or in other terms, we can say that there exists at least one map where the robot is able to detect every possible obstacle in that map. Let's give another example now. And let's say that the proposition where I want to start is that let's say every obstacle is either circular or square. Okay, let's translate this into formal language. For every obstacle O, let's say that we will translate this quality of being circular into a predicate, which I'm going to call C of O, because in fact this is a predicate with parameters O, which is the obstacle, and this predicate of being square as a predicate S of O. So we can say that P can be expressed formally as, for every possible O, it must be C of O or S of O, which is to say that obstacle must belong to one of these two classes, circular or square obstacles. And now we proceed with the negation of P. The negation of P will be there exists at least one obstacle such that not C of O or S of O. And now we can simply apply the rules for the negation of a connective and say that this is just like saying not C of O and not S of O, which is just another way of saying that there must be at least one obstacle which is not circular nor square, can be any other shape. In fact, we know that an obstacle like this is not even a square, not a circular object. As a final example of binary operator, let's consider the implication between proposition. So the implication is another example of binary operator. Now, given two propositions P and Q, the implication is a new proposition represented with an arrow. Okay, so this is the new proposition, which represents the fact that whenever P is true, then Q must be true. So in other terms, we can say that the fact that P is true is a sufficient condition to deduce that Q is true. Now, if this happens, the implication is true itself. If instead P is true and Q is false, then that means that the implication is false. So let's represent this with a truth table as always. So we have for P two possible values, true and false. For Q, two possible values, true and false. And as always, let's build the truth table. So we said that if P is true and Q is true, the implication is true. If P is true and Q is false, the implication is false. This is just like saying it is not true any longer that P is a sufficient condition for Q. If instead P turns out to be false, surprisingly, we can say that the implication is true in any case. So, in other words, this last column can be summarized in Latin, says that ex falso quod libet, meaning that from false assumption, which is in this case P being false, you can deduce anything. Okay. Okay, so in any case, if you start from a wrong assumption, any possibility, anything can be derived from that, and the implication is always true in any case. There is another implication, which is with the double arrow, starting from P and Q. It is represented in this way, and it is so-called the double implication. Double implication. And this double implication is true if and only if both of proposition have the same truth value. Let's use a truth table to represent all possible combination, as always. So in this case we have that if P is true, the double implication is true if and only if Q is true. So we can have a true value here, and the same way the implication is true if and only if both P and Q are false. Instead, if one of these is true and the other one is false, the double implication is false. As an exercise of the things that we said so far, let's try to rewrite P and Q, the implication P implies Q, by just using the symbols and, or, and not. In other words, we would like to represent the same truth table P implies Q, which again is this one. Let me copy this one. So we would like to represent this. Okay, so this is the truth table of P implies Q, but without using the arrow symbol, by just using the symbol and, or not. To do this, let's look a little bit more in detail at this table. Okay, so in this table we realize that when Q is true, we always get a true value no matter what P is going to be. So it is possible that we can represent the implication P implies Q as something like with an or connective with the Q, because whatever is the first element, we still don't know, but the second element being a Q, even if the first element, no matter what the first element is going to be, if Q is true, well, this implication is going to be true. So this seems to be a reasonable choice. However, let's also look back to the table, and we realize that for example, when P is false, the implication turns out to be false no matter what Q is going to be. So we can say that if we put not P here, this seems to be a good way of representing just the same table. So let's try this. If we have, let's say we have P here, we have true, false, Q here, true, false, and as always, let's build the truth table with these values. Okay, let's verify what happens. Well, if Q is true, and we are now in this position, then when Q is true, no matter what is going to be the other term, we always get a true value. P is false. If P is false, that means that not P is true. So no matter what Q is going to be, we always get a true value here. So we get a true. So we only need to verify now what happens when P is true and Q is false. Well, in that case, of course, we get a false because both Q and not P are going to be false. So in that case, clearly we get and we verify that we have obtained exactly the same truth table, which means that this is just a consistent way of representing the implication. So this implication is just like this. Right. Say now we can try to build the negation of an implication now, because let's say that we start from P implies Q. Okay, and let's suppose that we want to build the negation of this. Well, we can now resort to the usual rules, because now we can express P implies Q as not P or Q, and this is just applying the usual rules. This is not P and not Q, which means P and not Q. So we have obtained now a new version of the negation of a proposition. As a final list of examples of application of all these ideas, let's write some propositions in terms of numbers. Let's say that we have for every x in z, which means for every assigned integer, x larger than or equal to 3 implies that x to the square is larger than or equal to 9. Well, this is certainly true. Okay, you see that we started from this, that is clearly a predicate, but when using the universal quantifier, we have obtained on the left hand side a proposition that is just a proposition that implies another proposition, because of course x squared larger than or equal to 9 by itself would be just a predicate, but together with the quantifier, for every x it becomes another proposition. So we can definitely say that this implication is true. Another proposition would be for every x that belongs to z, x larger than or equal to 3 implies that x squared larger than or equal to 4. And also this is true because we are just limiting ourselves to the integers, and every integer that is larger than or equal to 3 has a square that is larger than or equal to 4. What happens if instead we say for every x in z such that x is larger than or equal to 2, can we say that the cube, x to the cube, is larger than or equal to 6? Yes, because clearly again we are limiting to just the integers, so the only integers that we will consider are 2, 3, and starting from 2, the cube of 2 is 8, which is larger than or equal to 6. So yes, this is another implication which is definitely true. Let's consider now the following proposition. For every x in z, x is larger than or equal to 2 if and only if x to the cube is larger than or equal to 6. Is this true or false? Well, this is certainly true because definitely the implication from the left to the right is correct, because as long as x is larger than or equal to 2 and it is in the integer set z, you can only consider 2, 3, 4, and therefore the x to the cube is larger than or equal to 6. That is correct. But what if we consider now the opposite arrow? Can we say that if the cube is larger than or equal to 6, then it must be x larger than or equal to 2? Yes, because all possible cubes of integer values, they will start from 8, so that means that x has to be larger than or equal to 2. So again, this is another true proposition. Let's now rewrite this proposition, but within a different context. Can we say that for every x into the real numbers, x larger than or equal to 2 if and only if x to the cube is larger than or equal to 6? Well, certainly the one arrow is true. So we can say that if x is larger than or equal to 2, then x to the cube is larger than or equal to 6, even in the real numbers, because every number to the right of 2 will give rise to a cube which is larger than 8, therefore is larger than 6. But the other arrow, clearly this is a false implication. Why? Because we can provide an example of a number that has x to the cube larger than or equal to 6, but it will be to the left of 2. For example, x equal to the cube root of 7. Okay, so if we look at this, this is a number that is on the left, basically, of 2, and still we have that x to the cube is larger than or equal to 6. So clearly this is a false implication. Okay, now let's conclude this lecture on elementary logic with a few rules to remember. Whenever we want to show that for x that belongs to some set within some context, p of x implies q of x is true. In other terms, if we want to prove that p of x is a sufficient condition for q of x, well then we need to provide a proof. So it is not enough to show that it is valid for some values of x. Instead, if we want to prove, so if we want to show that for every x belonging to some set, p of x implies q of x is false, then it is sufficient to find some value x star that belongs to the same set such that P of x implies Q of x is false. I just want to give now a formal proof of this. So we are basically saying that not for every x that belongs to some set, P of x implies Q of x. So we are saying that the negation of the proposition for every x, the implication P implies Q is true. Well, this, by just applying the use of rules, what we know that we need to invert the quantifiers. So that is just like saying there exists an x that belongs to some set such that not P of x implies Q of x, which is just like saying there exists an x that belongs to some set such that P of x or not Q of x. For example, an example of this would be if I say that for every x that belongs to z, x to the square is larger than or equal to 9 implies that x is larger than or equal to 3. Well, this is clearly false, and we just need to provide one example of this. And an example would be x equal to minus 25. In fact, minus 25 to the square is larger than or equal to 9, but minus 25 is less than or equal to 3, right? So with this, we can summarize our review of elementary logic. Next time, we'll start lecture 2 and we'll pass to natural numbers. Thanks for listening. Hope you enjoyed me for that. See you next time.